Okay, I'm back. I'm going to actually did the articles with ChatGPT, and I'm going to review them and rewrite them in the parts that I think that are necessary. I'm gonna start with the Fermat's little theorem and then go over the other ones. I think I'm gonna watch these videos as well and read articles. But first, let me read this here because I haven't read it yet. I'm gonna put some music as well. Fermat's little theorem is a fundamental theorem in number theory that is named after Piet de Fermat. Not sure how to just say this. French lawyer and mathematician. Let's check on Wikipedia. Pierre de Fermat. French lawyer and mathematician. So he was a lawyer, according to Wikipedia. Go back. The theorem is a simple yet powerful tool that helps to prove the primality of numbers and is widely used in cryptography, computer science, and other areas. On primality. Statement of the theorem. The statement of Fermat's little theorem is quite simple. If p is a prime number and a is an integer, any integer not divisible by p, then a elevated by p minus 1 is equal to 1 mod p. They're getting the remainder of the division is 1. In other words, if you take any integer a that is not a multiple of a prime number p and raise it to the p minus 1 power, then divided the result by p, the remainder is always 1. It's kind of obvious though, isn't it? Because you're elevating the number by 1 minus. Maybe it's not so obvious actually. The proof of Fermat's theorem is based on modular arithmetic. If A is not divisible by P, then we can define the set H modulo P. This set contains P minus 1 distinct elements, since if 2 of them were congruent, say if I is less than J, and J minus I, A equals 0 mod P. But since, I'm gonna change this stuff here. Since A is not divisible by P, this implies that J minus I is divisible by P, which contradicts the assumption that J between I and P minus 1. It's also clear that none of the elements of the set is equal to 0 modulo P, because each element of the set is congruent to one of the numbers 1, 2, 3, P minus 1, and no 2 are congruent to the same number. Now we multiply all the elements of the set together and obtain this. The left hand side can be written as this. I'm gonna have to change this stuff here. I'm gonna write it in a way that is not like this way here of like I don't know how to describe it, but I hate this way of that people write this stuff. Seems like it makes it harder to understand. I wanna write it as if I was explaining to someone. Yeah, I'm gonna watch the videos, understand more.
Here are the questions I'm going to be doing today. The first thing I need to point out is that this is not a video about Fermat's last theorem, the famous last theorem. If you're interested in that, I'll put up a link and you can go to my video on the theorem. It's really a beautiful interplay between modular forms, analytic curves, and my video will take you to the point where you can get that sort of overview. So check that out if you're interested. The other thing I should say is that Fermat's little theorem concerns itself with modular arithmetic. So if you don't understand this sort of thing that's on the screen now, then have a look at my video, Modular Arithmetic Made Easy, and then come back to this video. Now, Fermat's little theorem concerns about Fermat's last theorem. Over the last 300 to 400 years, it's encompassed some fantastic mathematicians, some new mathematical concepts, some intrigue, and a little bit of controversy as well. What I'm going to do today is precisely what I've said in the title. This is an introduction, so it's pretty basic level, and I'm going to confine myself to the proof of Fermat's last theorem. I'm going to do this in 3 sections. Firstly, what are we trying to prove? Secondly, a high-level overview of the proof. And then finally, I'll explain some of the characters or concepts that appear in that high-level overview of the proof. So let's start with what we are going to prove. It's very easy to find two numbers that are square numbers, but when we add them together, we get a square. So for example, 3 squared plus 4 squared equals 5 squared. Fermat's last theorem says that you can't replace the 2 with any higher number. So it's impossible to get 2 cubes that are added together to get a cube. It's impossible to get 2 fourth powers that add together to get a fourth power. And take any number greater than 2. It's impossible to take 2 100th power numbers and add them together and get a 100th power number. So now, let's go on to the second part, which is a high-level overview of the proof. The first thing I want to do is simplify the problem a little bit. It was pretty quickly proven that Fermat's last theorem is true in the case of cubics and 4 powers. When someone came along to try and prove it for 6 powers, which we've got down the bottom there, it was pointed out that a 6th power is itself a cubic. So I could rewrite this last line here, a squared or cubed plus b squared or cubed, etc. Now, since we've already proven that you can't sum 2 cubes to get a cube, that immediately knocks out the 6th power case. In fact, it knocks out every case where the power is divisible by 3. And that one before we saw before, the one a to the 100th plus b to the 100th, well, that can't be true because 100th is itself a 4th power. So if you follow that all through, it tells us that we really only need to look at the prime powers, not every power. So if we go back to our original problem, it would suffice to just change this number n to a prime p. So we're continuing to work our way through a high-level overview of the proof, and we've just established that we can simplify the problem a little bit. Now, there are many ways to prove things. The proof of Fermat's last theorem is a proof by contradiction. And I just want to go through a very simple example of proof by contradiction so that we can then better appreciate and understand the high-level overview of the proof of Fermat's last theorem. So here's a trivial example. Theorem: there are an infinite number of odd numbers. So let's look at the proof. We start out by supposing to the contrary that there are a finite number of odd numbers. So we haven't proven that, we're just making that supposition. Now we list a whole lot of logical statements that follow from our supposition. So if there are a finite number of odd numbers, then we can say, then we can list all the odd numbers in ascending order. 1, 3, 5, all the way up to m, where m is the largest odd number. That immediately follows from our supposition. Then we make another logical statement. Consider the number m plus 2. It is an odd number, must be odd because it's 2 more than m, which is odd, and it's bigger than m. So that follows from the previous logical statement. And now we have a contradiction. This contradicts the statement that m is the largest odd number. We just said that m was the largest odd number, now we've shown that there's a bigger number. So the only thing that can be wrong here is the supposition, because everything else is just logical statements, which must be correct. So the supposition that there are a finite number of odd numbers is false, and therefore there are an infinite number of odd numbers. Okay, now we're ready for a high-level overview of the proof of Fermat's last theorem. We want to prove that Fermat's last theorem is true, so we're going to suppose, to the contrary, that Fermat's last theorem is false. That is, for some a, b, and c greater than 0, and some prime p greater than 2, we have that a to the p plus b to the p equals c to the p, and that's what it means for Fermat's last theorem to be false. It then logically follows that the elliptic curve, y squared equals x times x minus a to the p times x plus b to the p, has no associated modular form. That directly follows. But all elliptic curves have an associated modular form. This is the thing that Wiles and subsequent mathematicians proved. So here we have a contradiction. We're saying that all elliptic curves have an associated modular form, but we've got an example above of an elliptic curve that has no associated modular form. So because of this contradiction, we can only surmise that our initial supposition is false. And that means that Fermat's last theorem must be true. Now we move to the last section, which is the important concept, and here I want to just try and explain what some of these terms mean. What is an elliptic curve? What is a modular form? And what does it mean for an elliptic curve to be associated with a modular form? For our purposes today, elliptic curves are any curve of this form here, where d, e, f, and g can be an integer. However, we specifically exclude curves that have custarly sharp points and also curves that intersect themselves. And so we're typically left with these two sorts of curves, this sort and this sort here. So the curve that we mentioned in the proof, this one, falls into the category of an elliptic curve. Just for example, let's make a equal 2, b equal 3, and p equal 5, and let's put up a graph of what that curve looks like. So let's move on to the second important concept, and that's the idea of modular forms. So many people, when I mention the word function, will think of something like fx equals x squared. And here they're thinking of x being maybe a counting number, say 3, or an integer, say minus 4, or a fraction, say a half, or an irrational, say the square root of 2. But we can extend this concept to complex valued functions. So here's the complex plane, and here we have a number, 1 plus I, and over here we have the result of applying a function to a point z on the complex plane. And if the function was, say, f z equals z squared, then this z over here, which is 1 plus I, would be squared, and that turns out to be 2i, so it would end up over here. And this function could apply to every point on the complex plane, so every point on the complex plane over here would be mapped onto another point on the complex plane here. Now for modular forms, for reasons that we're going to now, just use the top half of the complex plane. And modular forms are functions that have this property that for some integer k, we have that f of az plus b divided by cz plus d is equal to cz plus d all to the k times fz. This is for all z, and for all integers a, b, c, d, with ad minus bc equals 1. So this is, to go back up here, if this was the point z, we're saying this point over here may be az plus b divided by cz plus d. When we map these 2 points using the function, we get these 2 points over here. And the modular form has a very definite relationship between these 2 results over here. And this applies for every value of z. So here's an example. We may have a function such that f of 3z plus 1 divided by 2z plus 1 equals 2z plus 1 squared times f of z for all z. And this would be a modular form of weight 2. We say 2 because we've got a 2 up here. Now for what was used for Fermat's last theorem, there was interest in modular forms with an additional condition, and that revolves around the value c. So here's an example where we might restrict ourselves to where c is multiples of 11. So that means that this equation would apply for all z, and also this equation would apply for all z. Remember, we still must have that ad minus bc equals 1. And this is a modular form of weight 2 because of the 2 that we talked about before, but we would now say that it's a modular form also of level 11. So now we turn to the final important concept, and that is the statement in the proof that all elliptic curves have an associated modular form. This is really amazing. Two similarly unrelated things, elliptic curves and modular forms, and there is some sort of link between them. So what is this association? And this actually is this final part, all elliptic curves have an associated modular form, is what Andrew Wiles and subsequent mathematicians have proven. I haven't actually met Andrew Wiles, although I did have dinner with someone who's got an office near him, and he said Andrew came in one day and said he'd solved Fermat's last theorem. So that's my brush with fame. The other one, I suppose, is I've got a collaboration distance with Andrew Wiles before, because I've jointly published a paper with the mathematician Igor Shalinsky. He's published with Friedlander, he's published with Rubin, he's published with Wiles. So that's my brush with fame. So now let's have this elliptic curve up here. I'm going to do this by example. Here's an elliptic curve, and let's just quickly get up a graph of it, and we can see that it is a genuine elliptic curve. It doesn't have a cusp, and it doesn't intersect with itself. And what we're interested in is solutions to this problem, integer solutions. But we're not going to use all integers, we're just going to use a limited number. This is the area of modular arithmetic, or clock arithmetic, some people call it. And it's the idea that if I ask you what's 3 hours after 10 o'clock, you're not going to say 13 unless you're in the military. You're going to say it's 11, 12, 1 o'clock. So in the clock world, 10 plus 3 equals 1. Now, what I'm going to show you here applies to prime numbers. So I'm going to do the first one in a bit of detail using the prime number 3. So we're in modulo 3 land, all we have the numbers 0, 1, 2. So the question is, how many solutions are there to the elliptic curve using 0, 1s, and 2s? So there are 4 solutions. Actually, here are the 4 solutions. And I'll just show you with, say, x equals 2y equals 2y, that's a solution. So here are some calculations where you can see that after we go through looking at the left and the right hand side and applying the rule that you can only have 0, 1, and 2. So we're interested in remainders of numbers. If they're over that, you can see that in fact it is a solution. So we've got the prime of 3, and we've got 4 solutions to the elliptic curve. So now let's introduce the modular form. This is a function, so it's quite a lot to look at. The first thing is I've simplified it by using q to replace e to the power of 2 pi I z. So there is a z on the right hand side, just buried in all the q's. And you can see this is a complex valued function. We feed in a z, a complex number, and what comes out of it will be a complex number. And there's a bit of a pattern as you go across. We've got here 1, power of 2 is 1, then 11, 2, and then 22, 3, and then 33, and on it goes. This turns out to be a modular form of level 11, so it satisfies those conditions we saw before. Now when we expand this out, we can collect all the similar terms, or similar powers of q, so we get q minus 2q squared, and on it goes. And we can read off the coefficient of q cubed, and we're doing that because we're interested in this prime of 3, and we get -1. So it turns out that if we want to know the number of solutions to the elliptic curve modulo 3, then we can take the 3, and we can subtract the coefficient in the modular form. So what I'm saying is there are 4 solutions, and 4 equals 3 minus -1. So now let's have a look at some others. I'll put up here 5 and 7, and I'll also just put up 101. And you can see that in all cases, if we take the prime number, minus the coefficient in the modular form, then we end up with a number of solutions for the elliptic curve, modulo that prime. And this works for all primes except 11 because it's 11 modular form won't work necessarily work for that, but it'll work for all the others. And that's really the theorem that was proved that led to the proving of Fermat's last theorem. So I hope you've enjoyed getting this first sort of introduction to the proof of Fermat's last theorem, and I hope if you want to go a bit further, this will be a good foundation for you to explore a little bit more about concerns itself with modular arithmetic, where everything is done modulo p prime. And it turns out that there aren't that many questions that you can be asked about Fermat's little theorem. However, the generalization where we deal modulo prime or modulo a composite number is very, very important. It's called Euler's theorem. It's a very important generalization of Fermat's little theorem. So it's important to understand Fermat's little theorem to start with. So let's go to the first question. Now, I've generally never put on my videos something where it says state a theorem, but you can be asked in your test or exam to state a theorem. So if you want to get some marks for this sort of question, then you better know it. So the other reason I wanted to put this type of question up is that there are actually more than one ways of expressing Fermat's little theorem. So here's one that you'd see if you look on Wikipedia. Let p be any prime and a an integer, then a to the power p is congruent to a modulo p. Now, one I did at university was this one. Let p be any prime and a number between 1 and p minus 1. Then a to the p minus 1 is equivalent to 1 mod p. And the final one that you might see is this. Let p be any prime and a an integer with p not dividing a. Then a to the p minus 1 is congruent to 1 mod p. Now I'm going to use this middle one for most of the solutions for the following problems. So let's go on to question 2. It says fix p equals 7, so our prime is 7, and verify that Fermat's little theorem for a equals 3 and then for a equals 6. So here's the middle definition of the theorem that I had from the previous slide. So it's just a question of putting in these numbers. So we have, a equals 3 to start with. So we'll have 3 to the p minus 1, and p minus 1 is 6. So 3 to 6 is actually equal or congruent to 729, and that's congruent to 1 mod 7. In other words, the remainder when we divide 729 by 7 is 1. And if we want to do it then for a equals 6,
What's the difference between equal and congruent? This is the type of stuff I hate about mathematics. The annoying little things. So it's just an approximation, I think. Congruent is roughly equal.
we just repeat it. 6 to the 6 is congruent to 46,656. And once again, if we divide that number by 7, we get a remainder of 1. Now, if you were using, for example, that first definition from Wikipedia, that you get a to the p is congruent to a mod p, then you'd say 6 to the 7 is congruent to 279,936, which is congruent to 6 mod 7. Okay, so you might get this sort of idea. Use Fermat's little theorem to calculate 13 to the 36, modulo 19. Now, you can work this out in lot of ways don't involve Fermat's little theorem. If you're interested in that, have a look at my video, modular exponentiation made easy, where I go through 3 different methods. But here we're told you have to use Fermat's little theorem. So because 19 is a prime, we know from Fermat's little theorem that 13 to the power of 18 is equivalent to 1 mod 19. So we somehow have to use that, and we can recognise that 18 is half of 36, which gives us a bit of a clue. So we can do it this way. 13 to the 36 is congruent to 13. What's 36? It's 18 times 2. And now we can use the normal exponent rule. That's congruent to 13 to the 18 all squared. And we know that 13 to the 18 is 1 by Fermat's little theorem. So we've got 1 squared, which is equivalent to 1. That's that one. And what if we got this slightly different? It was now asking us to use Fermat's little theorem to work out 13 to the 39 modulo 19. And here we use a similar sort of trick, but here we recognise that 39 is, you can see down here, it's 2 times 18, which is 36, plus 3. And once again, we can use the exponent rules or power rules that you learned in high school to split that into the product of 13 to the 8 all squared times 13 cubed. And we've already worked out from question 3 that 13 to the 18 is 1, so we've got 1 squared times 2,197, which is 2,197. And when you work all that out, you see that when you divide that by 19, you get a remainder of 12. So that's it for Fermat's little theorem made easy. I hope you found it useful.
To make every possible style for each size. Starting with size 3, he begins by figuring out all possible styles. Well, each earring begins as a string of beads, and then the ends are attached to form a ring. So first, how many possible strings are there? Well, with 2 colors and 3 beads, there are 3 choices, each from 2 colors. So 2 times 2 times 2 equals 8 possible unique strings. And then he subtracts the strings which have only 1 color, or monocolored strings, since he's only building multicolored earrings. Then he glues them all together to form rings. He was assuming he'd end up with 6 different earrings, but something happened. He can no longer tell the difference between most of them. It turns out he only has 2 styles, because each style is now part of a group with 2 identical partners. Notice you can always match them up based on rotations. So the size of these groups must be based on how many rotations it takes to return to the original, or how many rotations to complete a cycle. So this means that the original set of all multicolored strings divides evenly into groups of size 3. Now, would this be true for other sizes? That would be convenient since he always wants the same amount of each style. So he tries this with 4 beads. First he builds all possible strings, and with 4 beads he can choose from 2 colors for each bead, so 2 times 2 times 2 times 2 equals 16. Then he removes the 2 monocolored necklaces and attaches all of the others to form rings. Now, will they form equal sized groups? Apparently not. What happened? Notice how the initial set of strings divides into styles. If strings are of the same style, it means you can form one into the other simply by grabbing beads from one end and sticking them onto the other end. And there is one style which only has 2 members, and this is because it's built out of a repeating unit of length 2. So only 2 rotations are required to complete a cycle. Therefore, this group only contains 2. He cannot split them into an equal number of styles. What about size 5? Will they break into equal number of each style? Wait, suddenly he realizes he doesn't even need to build them in order to find out. It must work, since 5 cannot be made out of a repeating pattern, because 5 cannot be broken into equal parts. It's a prime number. So no matter what kind of multicolored string you start with, it will always take 5 rotations or bead swaps to return to itself. The cycle length of every string must be 5. Well, let's check. First, we'll build all possible strings and remove the 2 monocolored strings. Then we separate the strings into groups which belong to the same style and build a single earring for each style. Notice that each earring rotates exactly 5 times to complete a cycle. Therefore, if we glue all the strings into rings, they must split into equal-sized groups of 5. Then he goes one step further. Currently, he's only using 2 colors, but he realizes this must hold with any number of colors, because any multicolored earring with a prime number of beads, p, must have a cycle length of p, since primes cannot be broken into equal-sized units. But if a composite number of beads are used, such as 6, we will always have certain strings with shorter cycle lengths, since it's actually built out of a repeating unit, and therefore will form smaller groups. And amazingly, he just stumbled onto Fermat's little theorem. Given a colors and strings of length p, which are prime, the number of possible strings is a times a times a p times, or a to the power of p. And when you remove the monocolored strings, he subtracts exactly a strings, since there are 1 for each color. This leaves him with a to the power of p minus a strings. And when he glues these strings together, they will fall into groups of size p, since each earring must have a cycle length of p. Therefore, p divides a to the power of p minus a, and that's it. We can express this statement in modular arithmetic too. Think of it, if you divide a to the power of p by p, you will be left with a remainder a. So we can write this as a to the power of p is congruent to a mod p. And here we have stumbled onto one of the fundamental results in number theory merely by playing with beads.
I still don't understand.
Minus a strings. And when he glues these strings together, they will fall into groups of size p, since each earring must have a cycle length of p. Therefore, p divides a to the power of p minus a, and that's it. We can express this statement in modular arithmetic too. Think of it, if you divide a to the power of p by p, you will be left with a remainder a. So we can write this as a to the power of p is congruent to a mod p. And here we have stumbled onto one of the fundamental results in number theory merely by playing with beads. Fundamental results in a mod p. That's it. We can express this statement in modular arithmetic too. Think of it, if you divide a to the power of p by p, you will be left with a remainder a. So we can write this as a to the power of p is congruent to a mod p. And here we have stumbled onto one of the fundamental results in number theory merely by...
I don't understand.
Here are the questions I'm going to be doing today. The first thing I need to point out is that this is not a video about Fermat's last theorem, the famous last theorem. If you're interested in that, I'll put up a link and you can go to my video on the theorem. It's really a beautiful interplay between module forms, analytic curves, and my video will take you to the point where you can get that sort of overview. So check that out if you're interested. The other thing I should say is that Fermat's little theorem concerns itself with modular arithmetic. So if you don't understand this sort of thing that's on the screen now, then have a look at my video, modular arithmetic made easy, and then come back to this video. Now, Fermat's little theorem concerns itself with modular arithmetic where everything is done modulo p a prime. And it turns out there aren't that many questions that you can be asked about Fermat's little theorem. However, the generalization where we deal modulo prime or modulo a composite number is very, very important. It's called Euler's theorem. It's a very important generalization of Fermat's little theorem, and so it's important to understand Fermat's little theorem to start with. So let's go to the first question. Now, I've generally never put on my videos something where it says state a theorem, but you can be asked in your test or exam to state the theorem. So if you want to get some marks for this sort of question, then you better know it. So the other reason I wanted to put this type of question up is that there are actually more than one ways of expressing Fermat's little theorem. So here's one that you'd see if you look on Wikipedia. Let p be any prime and a an integer, then a to the power p is congruent to a modulo p. Now, the one I did at university was this one. Let p be any prime and a number between 1 and p minus 1. Then a to the p minus 1 is equivalent to 1 mod p. And the final one that you might see is this. Let p be any prime and a an integer with p not dividing a. Then a to the p minus 1 is congruent to 1 mod p. Now I'm going to use this middle one for most of the solutions for the following problems. So let's go on to question 2. It says fix p equals 7, so our prime is 7, and verify that Fermat's little theorem for a equals 3 and then for a equals 6. So here's the middle definition of the theorem that I had from the previous slide. So it's just a question of putting in these numbers. So we have, a equals 3 to start with. So we'll have 3 to the p minus 1, and p minus 1 is 6. So 3 to 6 is actually equal or congruent to 729, and that's congruent to 1 mod 7. In other words, the remaining one we divide 729 by 7 is 1. And if we want to do it then for a equals 6, we just repeat it. 6 to the 6 is congruent to 46,656. And once again, if we divide that number by 7, we get a remainder of 1. Now, if you were using, for example, that first definition from Wikipedia, that you get a to the p is congruent to a mod p, then you'd say 6 to the 7 is congruent to 279,936, which is congruent to 6 mod 7. Okay, so you might get this sort of idea. Use Fermat's little theorem to calculate 13 to the 36, modulo 19. Now, you can work this out in a lot of ways that don't involve Fermat's little theorem. If you're interested in that, have a look at my video, modular exponentiation made easy, where I go through 3 different methods. But here we're told you have to use Fermat's little theorem. So because 19 is a prime, we know from Fermat's little theorem that 13 to the power of 18 is equivalent to 1 mod 19. So we somehow have to use that, and we can recognise that 18 is half of 36, which gives us a clue. So we can do it this way. 13 to the 36 is congruent to 13. What's 36? It's 18 times 2. And now we can use the normal exponent rule. That's congruent to 13 to the 18 all squared. And we know that 13 to the 18 is 1 by Fermat's little theorem. So we've got 1 squared, which is equivalent to 1. So that's that one. What about if we got this slightly different? It was now asking us to use Fermat.
65. Although he was a lawyer, he loved mathematics, number theory in particular. One of his more famous results is now called Fermat's little theorem. Fermat's little theorem says that if p is a prime number, and p does not divide the integer a, then a to the p minus 1 is congruent to 1 mod p. Let's see some examples so you get a feel for what this theorem is actually saying. Consider the case where p equals 5. 5 is prime. Then 5 doesn't divide 2, so 2 to the 5 minus 1 is congruent to 1 mod 5, or 2 to the 4th is congruent to 1 mod 5. So if you divide 2 to the 4th by 5, you'll get a remainder of 1. Similarly, p does not divide 3, so 3 to the 4th is congruent to 1 mod 5. P does not divide 4, so 4 to the 4th is congruent to 1 mod 5. Now p does divide 5, so the theorem does not apply in this case. And in fact, 5 to the 4th is congruent to 0 mod 5. Let's keep going. 5 does not divide 6, so 6 to the 4th is congruent to 1 mod 5. We can use Fermat's little theorem here. 5 and 7 are relatively prime, so 7 to the 4th is congruent to 1 mod 5. Similarly, 8 to the 4th is congruent to 1 mod 5. 9 to the 4th is congruent to 1 mod 5. Now we get to 10. Once again, 10 and 5 are not relatively prime. 5 does divide 10, so the theorem does not apply here. And in fact, 10 to the 4th is congruent to 0 mod 5. And this goes on forever. Now, this may seem like a very specific theorem, that it doesn't have a lot of uses because look, all the exponents are 4. It turns out, though, you can use this in examples when the exponent is something else. Let me show you an example. Let's find the remainder when you divide 3 to the 100,000th power by 53. Now 53 is a prime number, and 53 does not divide 3. So by Fermat's little theorem, we have 3 to the 53 minus 1 is congruent to 1 mod 53. Or 3 to the 52nd power is congruent to 1 mod 53. Here's the trick. We're going to raise both sides of the congruence to a power. Now, 1 to any power is 1, so the right-hand side won't change. But the left-hand side, we're going to pick a number so that we get really close to 3 to the 100,000th power. And here's how we find out. We just do straight division. If you divide 100,000 by 52, you get a quotient of 1,923 and a remainder of 4. So we're going to raise both sides of the congruence to the power of 1,923. On the left-hand side, we multiply the exponents, and we get 3 to the 99,996th power is congruent to 1 mod 53. We're almost to 100,000 on the left-hand side there. So we're going to multiply both sides of this congruence by 3 to the 4th. That gives us 3 to the 100,000th power is congruent to 81 mod 53. Okay, we can simplify the right-hand side. 81 is congruent to 28 mod 53. So if you divide 3 to the 100,000th power by the prime number 53, you will get a remainder of 28. Let's now prove Fermat's little theorem. And before we give the abstract proof, I'm going to show you an example of how the proof operates, so you'll have an intuition for it. So then the proof will make much more sense. Consider the prime p equals 7. Every integer is going to be congruent to 0, 1, 2, 3, 4, 5, or 6 mod 7. Now, let's disregard 0. We're only going to look at the non-zero numbers. Consider the case where a equals 12. Look what happens if we multiply all these numbers by 12. We get 12, 24, 36, 48, 60, and 72. If you simplify these mod 7, you get 5, 3, 1, 6, 4, and 2. Notice it's just a rearrangement of the numbers 1 through 6. That's the trick that's going to be used, that if you multiply the congruence classes by a, it simply rearranges them. So now let's actually give a formal proof of Fermat's little theorem. So again, we assume that p is a prime number, and p does not divide a. Then every integer is congruent to one of the following: 0, 1, 2, on and on up to p minus 1. And as before, we're only going to focus on the non-zero ones, because 0 is the congruence class that contains all the multiples of p, and we're interested in numbers which are not divisible by p, which are not multiples of p. So we're only going to consider 1, 2, on and on up to p minus 1. Let's multiply all of these by the integer a. We get a, 2a, on and on up to p minus 1 times a. Now let's show this is nothing more than a rearranging of the congruence classes 1, 2, 3, on and on up to p minus 1. First, we're going to show that none of these are 0. If one of these were 0, that means p would have to divide it. So suppose r times a was congruent to 0. That means p divides r times a. Well, we know p does not divide a, and p can't divide r because r is less than p. So p cannot divide the product. So none of these are congruent to 0 mod p. Next, let's show that none of these are congruent to each other, so they're all distinct. Now let's show that none of these are equal to one another. So let's pick two different numbers from this list. One is r times a, and the other is s times a. Well, r and s are both greater than 0 and less than p. So we have 0 is less than r is less than p, and 0 is less than s is less than p. What we want to show is r times a is not congruent to s times a mod p. So let's look at ra minus sa, which is equal to a times r minus s. We know p doesn't divide a, so we have to ask, can p divide r minus s? Well, let's go back to our inequalities. We have 0 less than r less than p, and let's multiply the second inequality through by -1. That gives us 0 is greater than negative s is greater than negative p. Let's kind of flip this around so the inequalities line up. That gives us 0 is less than r is less than p, and negative p is less than negative s is less than 0. If you add these two together, you get negative p is less than r minus s is less than p. Now, r minus s cannot be 0 because we picked two distinct numbers, and they're between negative p and p, so p cannot divide. It cannot be a multiple of p. The only multiple will be in that interval 0, and because we picked distinct numbers, r minus s is not 0. So a to a, on and on, to p minus 1 times a is just a rearrangement of 1, 2, 3, on and on to p minus 1. So their products are going to be congruent to each other because they're just rearrangements of one another. That means that a times 2a times 3a, on and on, to p minus 1 times a is going to be congruent to 1 times 2 times 3, on and on to p minus 1, mod p. The left-hand side is p minus 1 factorial times a to the p minus 1 power. And the right-hand side is congruent to p minus 1 factorial. Now, p does not divide p minus 1 factorial, because p minus 1 factorial is a product of the positive integers less than p. So because p does not divide p minus 1 factorial, we can safely cancel it from the congruence. Remember, you cannot cancel a number from the congruence unless it's relatively prime to the modulus. So we can divide both sides by p minus 1 factorial, we can cancel that out, and that gives us a to the p minus 1 power is congruent to 1 mod p. And that proves Fermat's little theorem.
I understand what the theorem says, but I don't understand its explanations, because I don't understand the group thing that they talk about.
Mod 53. Okay, we can simplify the right-hand side. 81 is congruent. Let's now prove Fermat's little theorem. And before we give the mod 53. So if you divide 3 to the 100,000th power by the prime number 53,
I don't understand this part here.
I use Fermat's little theorem all the time when it comes to number theory type problems. And in fact, I've given a couple of proofs on the channel of this theorem. I gave the standard proof, which comes from an elementary number theory class, and I've also given like a geometric combinatorial proof as well. And so today I want to give another proof, and there's actually some motivation for saying lots of proofs of Fermat's little theorem. Well, first off, it lets you understand the theorem very well, and Fermat's little theorem is famous in that there have been many different proofs of this theorem proven, or I should say written. And so here we're going to look at an induction proof of Fermat's little theorem. So let's recall what FLT says first. So it says for all natural numbers a, and in fact it says for all integers a, but I'll let you guys extend this to integers, and primes p, we have a to the p is congruent to a mod p. This is a version of Fermat's little theorem. Sometimes it's written as a to the p minus 1 is congruent to 1 mod p if a is not divisible by p. But that actually extends very easily from this as well. Notice if a is not divisible by p, it has an inverse mod p, then we can just multiply both sides of this congruence by a inverse, and we get that other version. So the proof that we'll take will heavily rely on the following lemma. It says for all n between 1 and p minus 1, we have the binomial coefficient p choose n is congruent to 0 mod p. So let's do the proof of that first. So I first want to
Okay, so if it's not divisible, then it means that it has a remainder, so that's why you can define the set here. Contains p minus 1 distinct elements, because it's the multiplication of these times the number. Since if two of them were congruent, say I times a equals j times a mod p. So the congruence means that the remainder of one of the division of one of the numbers by p is equal to the other number, with j greater than I, obviously, because you have the remainder, and j minus I times a, which is the parameter here, the bigger one minus the other one, is equal to 0 when divided by p. I don't understand why. But since a is not divisible by p, because it's implying here in the beginning that it isn't, it means that j minus I has to be divisible by p, which contradicts the assumption. Okay, this assumption I get it because this is implied here, and then because there's only p minus 1 numbers, it has to be up to that number, so I understand this part. Which is 0 modulo p. Thus, each element of the set is congruent to one of the numbers, and no two are congruent to the same number. So it's pretty much going over the same explanation from the video of getting the factorial on both sides and then simplifying. Oh, that's a problem. I have to escape this. I should put this inside of a code thing. And this is factorial, so it was correct there. Then you simplify, and then you get the thing. So the thing that I don't understand is this transition here. This thing here. The set contains p minus 1 distinct elements, since if two of them were congruent, say, then why is j minus I times a equals to 0 when divided by p? Because you're dividing here. Oh, but that doesn't make sense. Oh no. No, yeah. Let me think. I get that it is just passing there and then making, but it's simplifying based on the equation here, but I don't understand like how does it work with the modular p here? Like it's passing this one to this side and then distributing a outside. But then why is it 0 there? I guess the problem is that I don't understand modular arithmetic really well. I think I'm gonna study this a little bit more.
Notice that p choose n is going to be a natural number for all n in the given region and for all primes p. Obviously, p doesn't have to be a prime here for this to be a natural number, but p does have to be.
This stuff about modular arithmetic has to do with the stuff that I was talking about before, where I realized that the Cartesian plane or any kind of plane is just a projection of perceptions, and functions is like an assumption of symmetry based on that perception. And it's very interesting. I remember when I read one of those documents, I think it was Vitalik, one of the documents by Vitalik, that he said that it is similar to an extension of, like it is an extension of arithmetic and is similar to the complex plane. And that also made me think that I understand this more. Maybe I can think about different ways to use this to think about mathematics in a different way. Because I didn't think about that before, where he said that like what you're doing in the complex plane, you're extending mathematics. So it's like and this is the stuff that I was talking about, where like the thing that I don't understand or that I couldn't think about is how would you create a different type of mathematics to explore something that goes beyond your current perception, so that you can try to understand things that are beyond the scope of what you project based on your perceptions. And the complex plane is one situation of that, I think. And this modular arithmetic is probably another situation of that, where you're extending arithmetic based on, like, you're keeping some of the rules the same, but then you change them in order to allow you to view things in a different way. It's very interesting. And I never heard of modular arithmetic until now.
Prime in order for this to hold. Next up, I want to notice the case when n is equal to 1 is easy because p choose 1 is equal to p, which is clearly congruent to 0 mod p. So we'll look at the case when n is bigger than 1. Okay, if n is bigger than 1, then n factorial is also bigger than 1, and we can make the following fairly simple observation, that n factorial does not divide p. Well, why is that? The only factors of p are 1 and p. That's exactly the definition of a prime. But n factorial is the product of everything between 1 and n, but n is less than p. So since n is less than p, you never achieve that other factor of p, that being itself. Okay, so now let's go from there. Let's take this and rewrite it via its definition. So p choose n is equal to p times p minus 1 times p minus 2, all the way down to p minus n plus 1, all over n factorial. Next, we'll put our two...
Also, the prime has to be bigger. So this is what this implies here. Yeah, obviously. But the numbers in the set are gonna be bigger than prime. Oh, yeah. Some of them.
facts together. So our first fact is that p choose n is a whole. So our first fact is that p choose n is a whole number, and our second fact is that n factorial does not divide p, but that tells us that n factorial must divide the rest of this stuff. So that's p minus 1 all the way down to p minus n plus 1. But then that means that all of this is equal to a natural number. So we'll call it m, which is a natural number, which means we can write all of this as m times p, which is congruent to 0 mod p. Okay, so that finishes the proof of this lemma, which is essentially all we need to prove this very quickly. So let's get to that proof. So now that we've got this proof of our lemma, we're going to prove Fermat's little theorem using induction. So let's start with our base case. And our base case will be the first natural number. In other words, a is equal to 1. But if a is equal to 1, that means a to the p is equal to 1 to the p, which is also equal to 1. But here we have equality between a and a to the p. But equality between a and a to the p clearly implies congruence mod p between a and a to the p. Equality is stronger than congruence. Okay, so next let's make our induction hypothesis. So that means we want to suppose for some b bigger than or equal to 1, we have the result holding. So we've got b to the p is congruent to b modulo p. And then next we want to consider b plus 1 to the p. So let's do that. So consider b plus 1 to the p. But via the binomial theorem, we can expand this fairly easily. So that's going to be the sum as n goes from 0 all the way up to p of p choose n times b to the n. Again, that's just by the binomial theorem. Next, I'll take out the 0th term and the pth term. Notice the 0th term will be p choose 0, which is just 1, b to the 0, which is 1. And then that pth term is p choose p, which is again 1, and then b to the p. So I've got 1 plus b to the p plus the sum as n goes from 1 up to p minus 1 of p choose n, b to the n. Okay. But let's see what our lemma shows us. Our lemma tells us that every term from the sum is congruent to 0 mod p. So that means this entire sum must in fact be congruent to 0 mod p. But then our induction hypothesis tells us that b to the p is congruent to b mod p. So that means we can take all of this and write it as b plus 1 mod p. So let's just reiterate what went on here. So the induction hypothesis, which I'll maybe underline in yellow, gave us this congruence, which I have in yellow. And then the lemma told us that all of the rest of this stuff, which might be bad, is actually okay because it's just 0 mod p. So in the end, we have b plus 1 to the p is congruent to b mod p, and that finishes this proof by induction. And that's a good place to stop.
Hey everybody, this
Are not divisible by p, which are not multiples of p. So we're only going to consider 1, 2, on and on up to p minus 1. Let's multiply all of these by the integer a. We get a, 2a, on and on up to p minus 1 times a. Now let's show this is nothing more than a rearranging of the congruence classes 1, 2, 3, on and on up to p minus 1. First, we're going to show that none of these are 0. If one of these were 0, that means p would have to divide it. So suppose r times a was congruent to 0. That means p divides r times a. Well, we know p does not divide a, and p can't divide r because r is less than p. So p cannot divide the product. So none of these are congruent to 0 mod p. Next, let's show that none of these are congruent to each other. So they're all distinct. Now let's show that none of these are equal to one another. So let's pick two different numbers from this list. One is r times a, and the other is s times a. Well, r and s are both greater than 0 and less than p. So we have 0 is less than r is less than p, and 0 is less than s is less than p. What we want to show is r times a is not congruent to s times a mod p. So let's look at ra minus sa, which is equal to a times r minus s. We know p doesn't divide a, so we have to ask, can p divide r minus s? Well, let's go back to our inequalities. We have 0 less than r less than p, and let's multiply the second inequality through by negative 1. That gives us 0 is greater than negative s is greater than negative p. Let's now kind of flip this around so the inequalities line up. That gives us 0 is less than r is less than p, and negative p is less than negative s is less than 0. If you add these two together, you get negative p is less than r minus s is less than p. Now r minus s cannot be 0 because we picked two distinct numbers, and they're between negative p and p, so p cannot divide it. It cannot be a multiple of p. The only multiple of p in that interval is 0, and because we picked distinct numbers, r minus s is not 0. So a, 2a, on and on to p minus 1 times a is just a rearrangement of 1, 2, 3, on and on to p minus 1. So their products are going to be congruent to each other because they're just rearrangements of one another. That means that a times 2a times 3a on and on to p minus 1 times a is going to be congruent to 1 times 2 times 3 on and on to p minus 1 mod p. The left-hand side is p minus 1 factorial times a to the p minus 1 power. And the right-hand side of this congruence is p minus 1 factorial. Now p does not divide p minus 1 factorial because p minus 1 factorial is a product of the positive integers less than p. So because p does not divide p minus 1 factorial, we can safely cancel it from the congruence. Remember, you cannot cancel a number from the congruence unless it's relatively prime to the modulus. So we can divide both sides by p minus 1 factorial. We can cancel that out, and that gives us a to the p minus 1 power is congruent to 1 mod p. And that proves Fermat's little theorem.
This is Paul. Welcome back to another lesson in cryptography. In this video, we're going to be talking about modular arithmetic. Modular arithmetic is a very fundamental component of cryptography, so it's very important that we understand what modular arithmetic is and how to use it before we ever start learning about cryptography. Here I have a statement, and what the statement says is it says 3 is congruent to 5 mod 2. So essentially what that's saying is in the world of mod 2, 3 and 5 are equivalently the same thing. So how exactly does that work? Well, let's look at this number line right here. We'll go ahead and place 3 on this number line. So there's a 3, and now we'll go ahead and place 5. And so now we have the numbers 3 and 5 on our number line. But 3 and 5 are two distinct numbers here. However, we're dealing with mod 2 in this case. So the 2 here in mod 2 tells us how many values we can have in mod 2. That means there's only 2 values in mod 2. So for every mod, the value starts at 0 and it ends at one number less than the mod. So one number less than 2 is 1. So for mod 2, the acceptable values are 0 and 1. If we were dealing with mod 3, we would have 3 values to work with, starting at 0, then 1, and going up to
We're dividing the number on the right by the true there. I was reading this incorrectly. I was reading as if this number is equal to the remainder of this divided by this number. But is the other array is saying that the remainder of this is equal to the remainder of this divided by this thing here. So, oh, okay, now I get it. Let me think more about this. Okay, saying that j is bigger than I. So why is j minus I times a equals 0, the remainder? And saying that it's going to be divisible by p, but because I think I understand. Is the remainder of them is the same? It's saying that is not though. And the remainder of them is the same, then you have to assume that either one is going to be divisible by p. And the multiplication here. It's saying that if you divide two of them by mod p, they would have the same remainder. If that was the case, then if you subtract one from the other and multiply by a, the remainder should be 0. But that's not the case, because then this assumes that the numbers are smaller, that are bigger than p minus 1, because they have to be divisible by p, and a is not divisible. But I don't understand why j minus I here. I don't understand why this implies this thing here. Why this implies this. I mean, they're the same. But it's saying that it doesn't imply that, though. Saying if they were congruent, it would imply that. No, because a is not divisible by p, and j minus I contradicts the, if you were divisible, you would contradict the, because one of them would have to be greater than p, so that this part here was divisible by p, and a is not divisible because that's what's assumed here to make the set. Yeah, I don't get it. Like there's nothing that makes me think that this should imply this. Like I don't see the connection there. Why can you assume that this thing implies this thing? They're both divisible by p, and they're congruent. Yeah, I don't understand.
To 2, 0, 1, and 2, 3 values in mod 3. 0 and 1 gives us 2 values for mod 2. If we wanted to take this further, we could take a look at mod 9, and the acceptable values for mod 9 would be 0 all the way up to 8, giving us 9 numbers. So I think you guys can see the pattern here. The mod number tells us how many values we have in our mod, and the highest number of the mod is always 1 less than the mod itself. So 3 goes up to 2, 2 goes up to 1, 9 goes up to 8. So how do we apply these values to our number line here? Well, we start at the 0, and for the moment we'll look at mod 2. So the possible values we can have for mod 2 are the numbers 0 and 1. So we start at 0, and then the next number would be 1. So then we would want to put a 2, but 2 isn't one of the acceptable values. So we switch back to the beginning. So this becomes 0, 1, 0, 1. So 3 has the value 1 in mod 2, and 5 also has the value 1 in mod 2 as well. So therefore, 3 and 5 essentially have the same value when we're dealing with mod 2. We can also apply this to negative numbers as well. So following this pattern, negative 1 would have the value of 1 in mod 2, negative 2 would have the value of 0 in mod 2, and negative 3 has the value of 1 in mod 2. So in mod 2, negative 3 is congruent to positive 3, and negative 3 is congruent to 5, because both negative 3, 3, and 5 correspond to the number 1 when we're dealing with mod 2. Let's take a look at this with mod 3 now. So when we want to plot the numbers for mod 3, we're going to use the same approach that we used when we plotted the numbers for mod 2. So 0 always maps to 0, and then we start counting up in mod 3. So 1 is 1, 2 is 2, and then we would want to do 3 next. But when we're dealing with mod 3, our only possible values are 0, 1, and 2. So since we've already got to 2 here, we start over at 0 again. So 4 becomes 1, and 5 becomes 2. So we just create this pattern all the way across the number line. 0, 1, 2, 0, 1, 2, 0, 1, 2, and it just keeps repeating. So therefore, all of the integers on the real number line will map to 0, 1, or 2 when we're dealing with mod 3. We can also take this in the negative direction as well. So going backwards now, starting at the other end, 2, 1, 0. So negative 3 is congruent to 0 in mod 3, and positive 3 is congruent to 0 in mod 3. Notice how I went backwards here in the negative direction. But if we read this left to right again, we continue the same pattern. 0, 1, 2, 0, 1, 2, 0, 1, 2, and it just keeps repeating. If we're looking at 3 and 5 in mod 3, 3 and 5 are not congruent. 3 is congruent to 0, and 5 is congruent to 2. So therefore, we would say 3 is not congruent to 5 when we're dealing with mod 3. But we can say 3 is congruent to 0 in mod 3, and we can say that 5 is congruent to 2 in mod 3. So this is probably a good stopping point for now for an introduction to modular arithmetic. In the next videos, I'll be covering how to add, subtract, multiply, and divide with modular arithmetic as well. So stay tuned for those videos. Thank you guys for watching. Have an excellent day, and if you haven't already, don't forget to subscribe.
This video is sponsored by Brilliant.
Pick any integer and raise it to the 5th power, and the 1's digit will remain the same. Or take any prime number besides 2 and 3, square it, and then subtract 1. That number will guaranteed be divisible by 24. In fact, take any prime number squared and subtract another smaller prime number squared. So long as they're both greater than 3, that result will be divisible by 24. These are a few examples of problems from a number theory book that I spent a few months going through after gaining an interest in the math behind cryptography. Although there's a lot of detail in this branch of math, I want to show you guys some of the very basics in a visual way that isn't as common to see. So let's start here. If you wanted to determine whether 119 was prime, or whether no integers go into it evenly besides 1 in itself, how many divisors would you have to check? Like 2 doesn't go into 119, of course. Then if you went to your calculator and did 119 over 3, you'd see it doesn't go in evenly either. But how many numbers do I have to try before I can say it's prime or not for sure? The answer is sort of 4, but really 2. And by that I mean hand me a calculator, and I'll tell you in 2 tries whether 119 is prime or not. And we'll see why in a second. Now, these right here are the first several prime numbers. Nothing goes into them but 1 in themselves. And there are infinitely many of these. All other numbers that don't appear here, like 30, are made up of 2 or more of these primes. So instead of seeing a number for what it is, you can see it as what it's made up of. And no, there's only one way to make up a composite number using primes. Like as a new example, 3 times 7 times 11 is 231. These 3 numbers are prime, and thus the only ones that go into 231. From this I can tell you that 231 is divisible by combinations of these primes, like 21 or 77 or 33. But it's not divisible by 13 or 17 or 19 and so on, because like we said, there's only one possible representation. So now if you were asked, like, is 18 factorial divisible by 23, you can immediately say no, because whatever 18 factorial is, it's made up of primes that are all less than 18, like 17 and 13 and 11 and so on. Then any composite such as 15 are something made up of primes less than that, or 5 and 3 in this case. You won't find a prime greater than 18 in here. And since there's only one way to represent 18 factorial as a multiple of primes, just like any other number, then I can safely say it's not divisible by 23, or 29 or 31, and so on forever. With that background, you now should be okay with this theorem. For any composite number x, one of its prime factors must be less than its own square root.
To see why this is true, let's just see what would happen if it wasn't. For example, the square root of 129 is about 11.35. Now let's just say there are two prime factors of this number. The theorem above says one of those must be less than 11.35. Because if that weren't the case and they were both greater than 11.35, like let's say 13, the next prime number up, we've already exceeded 129 when we multiply those. So one of the primes has to be smaller than that square root. In this case, 129 is made up of 43 and 3, which goes with what the theorem says. Now if we take the number 119, the square root of that is about 10.9. Thus, if it is composite, one of its factors must be less than 10.9. And the only primes less than that are 2, 3, 5, and 7. I know 2 and 5 don't go into 119 just by looking at the ones digit, of course. So really, I just need to check two numbers. 3 does not go into 119, but 7 does. Thus, it's composite, and it only took 2 tries to figure that out. And now if you wanted to determine whether 901 is prime, you know you only have to check primes less than the square root of that, or about 30, which is only 10 numbers, or really 8 if you exclude the obviously wrong ones of 2 and 5. But now I want to show you something called wheel math. Okay, not really, it's called modular arithmetic, but I'm gonna stick with wheel math to keep this video as visual as possible. First, I'm gonna make a wheel of numbers, and to begin, it'll have 7 spokes or sections to it, although I could pick any number I wanted. So let's see what this tells us. The wheel starts at 0 and goes around to 6, and then jumps up to 7 and continues going around in the spiral. One thing to note is that as we move up some section, we simply are adding 7 each time, which means this section starting at 0 is the numbers divisible by 7 section. Another thing to notice is this tells us the remainders when we divide by 7. Like if I have 15 guests over for a party, I want to make teams of 7, I can make 1, 2 teams with 1 person left over, aka 1 is the remainder. And if I have 25 friends over, I can make 1, 2, 3 teams of 7, which would leave 4 left over. Any number that's divisible by 7, of course, would have no remainder. By the way, two values being in the same section, like 2 and 9, means they're congruent modulo 7. But again, I want to keep this video as visual as possible and hold off on all the official notation. Now, math on this wheel gets interesting. To start off, pick any two numbers, let's say 2 and 3, then add them, and the result will of course be 5. But if we pick any two numbers on those same initial sections, like 9 and 17, the sum of 26 will lie on the same final section. And the same thing happens with multiplication. 2 times 3 is of course 6, so something like 9 times 17 must give us something on that same resulting spoke, in this case 153. Then if I add 1 to that, we get 154, taking us to the next spoke over. And now just by looking, I know that number is divisible by 7, since it's in that divisible by 7 section of the wheel. See, this is where it gets more interesting. Like since I know that 2 times 3 plus 1 is divisible by 7, I also know, let's say this time 16 times 24 plus 1 is also divisible by 7. And that's because these sets of numbers all lie in the same section on our 7-spoke wheel. And to continue with the basic arithmetic, this applies to exponents as well. 2 squared is of course 4, and this tells us that anything in this blue section squared will output a number in this green section, where we found the 2 and 4 respectively. So since like 16 squared is 256, I know I'm going to find that number further up this green section. This isn't deep math or anything, by the way. I mean, when we square some number x, it becomes x squared, of course. And when we take a number on that same spoke as x, which would just be the same thing plus some integer multiple of 7, and square that value, after some simplifying, it just turns into x squared plus an integer multiple of 7. Therefore, it's on the same spoke as x squared from above. And yes, this will work with any integer exponent, by the way. So now take a look at the number 1 on our wheel. Since 1 to any power, I'll choose 26, is itself, or 1, and therefore maps to its own spoke, I know that anything else in that section, like 15, will always map to the exact same section when you include any integer exponent. Thus, I know 15 to the 26, or any other integer exponent, has a remainder of 1 when divided by 7, since it'll be in that same section as 1. So now in a matter of seconds, you can answer some seemingly tough questions that you may not have been able to do a minute ago. Like, is 8 to the 167th minus 1 divisible by 7? This is actually really easy to do. I don't know what 8 to the 167th is, but I know 1 to the 167th is 1. Thus, 8 to the 167th will give us a value also in that same section, just higher up. Then when we subtract 1, as the question asked, we move one spoke over and land in the one where all numbers are divisible by 7. So the answer to the original question is yes, with no intensive work required. But here's the least intuitive property I'll discuss, which works since we're using a prime number of spokes, or 7 in this case. Take any number not divisible by 7, like 2, 5, 15, or whatever, and raise it to the 6th power, or 1 less than the number of spokes we have, and that resulting value will always land in the section that has a remainder of 1. This will always be the case with prime wheels. As in, if we had a 5-spoke wheel and took maybe 12 and raised it to the 4th, our prime number minus 1, the resulting value will definitely be in that same section as 1 as the remainder, just like before. And also, like we saw earlier, we can do fast math and say that 12 to the 4th minus 1 is divisible by 5, because it lands in the divisible by 5 section of this new wheel. This is Fermat's little theorem, again written like this. To break this down, it says that on a wheel with a prime number of sections, any number we'll call a raised to the power of our prime minus 1 will be in the same section as the number 1, so long as a is not divisible by the prime. So when asked something like what is the remainder when 2 to the 100 is divided by 101, it's actually really easy. Since 101 is prime, then anything that's not a multiple 101 raised to the 100th or that prime minus 1 will be in the same section as 1, and thus that will be the remainder. Another cool property that works for any wheel with a prime number of sections is that if you take any number, raise it to that prime power, or 5 in this case, the result will be in the exact same section. And this kind of answers what we saw in the beginning of the video. You'll notice that on any section, every other number has the same 1's digit since they're 10 apart. So like all these numbers are ones that end in 2 or 7. Now we just saw that any number to the 5th stays in its own section on this wheel. So doing that operation either keeps the same 1's digit or changes it by 5, such as 2 going to 7 or 7 going to 2. Except when you raise a number to the 5th, odds will stay odd and evens will stay even. Thus the second option isn't possible, and any number to the 5th will retain its 1's digit as mentioned in the beginning. Now if we make a wheel of 12 numbers, some cool things come from it. One thing to note is that all the primes show up on only 4 spokes. The only exceptions to this are the numbers 2 and 3, which are the only primes on these 2 right-hand spokes here. Again, this is nothing deep, as with most of this video, honestly. It happens simply because the primes that make up 12 are only 2 and 3. So in those sections, as we add 12 and move up our wheel, the resulting numbers will all be divisible by 2 or 3. In fact, all the sectors that consist of composite numbers start with a number divisible by 2, 3, or both. The sectors with primes, on the other hand, all start with a prime number or the number 1. So this isn't groundbreaking or anything, but I find it to be an interesting way to just look at numbers and primes. Then going back, if we multiply 2 primes together besides 2 and 3, the resulting value will also be in the same sections as the primes, just filling in some of the gaps. But the weirdest thing is that any prime number squared besides 2 and 3 will land in this section. This means any prime number squared minus 1 lands in the next spoke over, or the section where everything is divisible by 12. I mentioned this earlier, but an even stronger case where any prime squared minus 1 is divisible by 24. If you want to know why, just note that p squared minus 1 can be written as p minus 1 times p plus 1. And on a number line, we can write p minus 1 and p plus 1 around the original prime p. Now, since p is prime, then it's not even because it's greater than 2, meaning that p minus 1 and p plus 1 are even or divisible by 2. But every other even number is divisible by 4, so either p minus 1 or p plus 1 has a factor of 4. It's easier to see this with examples, like if these numbers were 30, 31, and 32, one of the even numbers must be divisible by 4, which 32 is. Then of 3 numbers in a row, one of them must be divisible by 3. It's not p, since p is prime, so it's gotta be one of the others. This means that 2, 3, and 4 are factors of p minus 1 or p plus 1, and those multiply to 24. Thus 24 is a factor of the original number. Now, earlier in the video, I talked about dividing a number by 3, and as I'm sure many of you know, when it comes to 9 and 3, divisibility is actually really easy due to a certain rule. The rule is if the sum of the digits of a number is divisible by 9, then the number itself is divisible by 9, and the same goes with 3. As in, 972 is divisible by 9 because 9 plus 7 plus 2 is 18, which itself is divisible by 9. The reason for this is I can write 972 as 900 plus 70 plus 2, which can break down further to 9 times 100 plus 7 times 10 plus 2. 100 can then be written as 99 plus 1, and 10 as 9 plus 1. Then if I distribute everything, we're left with this. These terms are both divisible by 9 due to the 9 and 99 of them. So in order for the entire number to be divisible by 9, the last terms combined must be, which are the digits of the original number. The slightly more official term for working with 9s, though, is the digital root. To calculate the digital root of a number, let me just show an example. If we want to find the digital root of 921, let's say, we just add the digits together, giving us 12. We then add those digits together, giving us 3. Once we're down to one digit like this, we have the digital root. The cool thing about this is that it tells us how far a number is from being divisible by 9, aka the remainder. In this case, we see that 921 minus 3 is divisible by 9, which you now also know is the digit summation. Another property if we go to Brilliant Sight is that digital roots do not change when you add or remove 9s from a number. So like we saw 921 has a digital root of 3, yet so does 9921, and 99,921, and so on. Adding 9s doesn't change anything. Which means this huge number's digital root is 3, and thus it is 3 away from being divisible by 9. And this just comes down to the fact that if we remove all the 9s, leaving us with 21, that's also 3 away from being divisible by 9. Then something even weirder is that digital roots multiply. As if you want to know how close this result is to being divisible by 9, you multiply the individual digital roots. Since these 9s don't matter like you just saw, we can remove them. This means the digital root of each number is 1, and thus when we multiply them, the final digital root is of course 1. So I don't know what this large value is, but I know if I subtract 1, it will be divisible by 9. And just because we've seen 24 come up in this video in a kind of surprising way, here's another example dealing with digital roots. These are the first 24 numbers of the Fibonacci sequence, if we exclude 0, where you add the two previous numbers to get to the next. And these are the associated digital roots. Strangely, the digital roots you see here repeat this pattern forever as you go through the Fibonacci sequence, reoccurring every 24 numbers. Not gonna go into more detail beyond that, but I just found it interesting. Now after all this, you may be saying, yeah, this can help me do fast math, but can it help me write secret codes? Okay, maybe you weren't thinking that, but still the answer is yes, like I briefly mentioned in the beginning. I've done an entire video on the math behind cryptography, and for those who just want to know how the things we saw here apply to encrypting messages, here's a quick explanation. First, just imagine a world before cryptography where you want to communicate with someone you've never met before, yet there's an eavesdropper in the middle of you two who can hear anything you say or see anything you do. My question is, how would you communicate a message to the other person secretly just by shouting over to them? You can communicate anything, a place to meet, a secret number, a secret phrase, or whatever, but the eavesdropper who can hear everything is not supposed to understand what you said. And assume you all speak the same language and none of you guys know each other. So see what you can come up with. Yeah, it's definitely not easy if you don't have time to communicate beforehand. But here's one thing you can do. Tell the person we'll be doing some math on a wheel with 17 sections, and we're gonna pick a base value of 5. I didn't have to pick these numbers, but I'm just using them for simplicity. So yes, you said this out loud, which means the eavesdropper will be in on everything so far. But then you tell the person to think of a secret number and don't say it out loud while you do the same thing. So let's say they choose 4 and you choose 3. Now you do that base value of 5 to the power of your secret number, which gives us 125, and then you find the smallest number on that section of the wheel. With 17 numbers, 125 will be in the same section as 6, and 6 is what you tell the other person. Then they do the same by calculating 5 to the 4th, which is in the same section as 13 on our wheel, and they tell you that value. So now the eavesdropper has these two values as well, but not the secret numbers. Lastly, you take their value of 13 and raise it to your secret number of 3, and again find where that is on our wheel, which is 4 in this case. The other person does the same, and they will guarantee get 4 as well. This number is then your secret key. We haven't shared a message really, but we have established a secret key that we can then use to encrypt messages. For example, now we could like shift the letters in our message by 4 to communicate, although no, that's not what modern cryptography does. What you saw was the basics of the Diffie-Hellman protocol, and the reason it works to establish a secret key is because it is easy to do the math you just solved forwards, but it's very hard for the eavesdropper to take the numbers he has and work backwards to figure out your secret numbers, and therefore the final key. Algorithmically, it would just take too long. Not with this example, but when dealing with numbers hundreds of digits long, going forward is doable fairly quickly, yet going backwards at the moment just isn't feasible in a short amount of time, so you can have a secure form of communication, even if someone's watching. But everything you saw was really just scratching the surface of this branch of math, but if you found this content interesting, I recommend checking out Brilliant's number theory course, where you'll learn a lot more. There you'll be taken through all the basics like you saw here, but they also include interactive exercises and show unique applications of all the underlying math in much more detail. This includes things like analyzing the trajectory of a pool ball on ideal tables or dimensions, or how to mathematically solve a number theory puzzle that was famously portrayed in the movie Die Hard 3. On top of number theory, they have differential equations, complex analysis, logic, and over 50 other courses to choose from that all come with practice problems and interactive exercises to ensure you fundamentally understand each concept before moving on. On top of this, they have daily challenges that turn learning into a habit, so you can look forward to learning a range of topics from quantum physics to geometry puzzles and more. So if you want to start right now and support the channel, you can click the link below, or go to brilliant.org/majorprep to get 20% off your annual premium subscription. And with that, I'm gonna end that video there. If you guys
I
enjoyed,
still don't understand this shit. It's because I'm tired already. I understand the theorem, but I don't understand the proof.
This video is sponsored by Brilliant.
At this part here, I don't understand. It feels like I'm missing something.
But now I want to show you something called wheel math. Okay, not really, it's called modular arithmetic, but I'm gonna stick with wheel math to keep this video as visual as possible. First, I'm gonna make a wheel of numbers, and to begin, it'll have 7 spokes or sections to it, although I could have picked any number I wanted. So let's see what this tells us. The wheel starts at 0 and goes around to 6. It then jumps up to 7 and it continues going around in the spiral. One thing to note is that as we move up some section, we simply are adding 7 each time, which means this section starting at 0 is the numbers divisible by 7 section.
This is really interesting though. I didn't catch this the last time. It goes around in a spiral. Very interesting. Because it makes me think about gravity. There's probably something to do with gravity. Like all these numbers must have to do with something fundamental of nature. It's interesting to think about, but it's very difficult and confusing. It's hard to understand.
Another thing you'll notice is this tells us the remainders when we divide by 7. Like if I have 15 guests over for a party, I want to make teams of 7, I can make 1, 2 teams with 1 person left over, aka 1 is the remainder. And if I had 25 friends over, I can make 1, 2, 3 teams of 7, which would leave 4 left over. Any number that's divisible by 7, of course, would have no remainder. By the way, 2 values being in the same section, like 2 and 9, means they're congruent modulo 7. But again, I'm going to keep this video as visual as possible and hold off on all the official notation. Now, math on this wheel gets interesting. To start off, pick any 2 numbers, let's say 2 and 3. Then add them, and the result will of course be 5. But if we pick any two numbers on those same initial sections, like 9 and 17, the sum of 26 will lie on the same final section. And the same thing happens with multiplication. 2 times 3 is of course 6, so something like 9 times 17 must give us something on that same resulting spoke, in this case 153.
This is what I don't understand. I don't understand the terminology he's using here. Why does it have to be 9 times 17 have to be here? Don't get it. Also don't understand this. 2 modulo 7.
And hold off on all the official notation. Now, math on this wheel gets interesting. To start off, pick any two numbers, let's say 2 and 3, then add them and the result will of course be 5. But if we pick any two numbers on those same initial sections, like 9 and 17, the sum of 26 will lie on the same final section. And the same thing happens with multiplication. 2 times 3 is of course 6, so something like 9 times 17 must give us something on that same resulting spoke, in this case 153.
Oh, I think I understand now. So he's just talking about the section and not talking about the levels. So he's saying that if you do some addition or multiplication, you're gonna find the section that all the other additions and multiplications are gonna be at, which is very interesting.
Then if I add 1 to that, we get 154, taking us to the next spoke over. And now just by looking, I know that number is divisible by 7, since it's in that divisible by 7 section of the wheel. See, this is where it gets more interesting. Like, since I know that 2 times 3 plus 1 is divisible by 7, I also know, let's say...
The thing is, like, realistically, you would have to calculate anyway, to know that is on the section. That's what... But actually not, because you can get two numbers here, and then you do a multiplication, find the number, then you automatically assume, then you can just do the addition to know that it is on... I think I got it.
Say this time 16 times 24 plus 1 is also divisible by 7. And that's because these sets of numbers all lie in the same section on our 7-spoke wheel. And to continue with the basic arithmetic, this applies to exponents as well. 2
I
squares...
think what is making it difficult to understand is that I have more stuff on my mind as well. It's kind of like, it's difficult to... And I notice this a lot of times because I'm thinking about the article here, so it's hard to pay attention to this and then think about how I'm gonna explain this thing here. That's the problem, I think.
Is of course 4, and this tells us that anything in this blue section squared will output a number in this green section, where we found the 2 and 4 respectively. So since like 16 squared is 256, I know I'm going to find that number further up this green section. This isn't deep math or anything, by the way. I mean, when we square some number x, it becomes x squared, of course. And when we take a number on that same spoke as x, which would just be the same thing plus some integer multiple of 7, and square that value, after some simplifying, it just turns into x squared plus an integer multiple of 7. Therefore, it's on the same spoke as x squared from above. And yes, this will work with any integer exponent, by the way. So now take a look at the number 1 on our wheel. Since 1 to any power, I'll just use 26, is itself, or 1, and therefore maps to its own spoke, I know that anything else in that section, like 15, will always map to the exact same section when you include any integer exponent. Thus, I know 15 to the 26, or any other integer exponent, has a remainder of 1 when divided by 7, since it will be in that same section as 1. So now in a matter of seconds, you can answer some seemingly tough questions that you may not have been able to do a minute ago. Like, is 8 to the 167th minus 1 divisible by 7? This is actually really easy to do. I don't know what 8 to the 167th is, but I know 1 to the 167th is 1. Thus 8 to the 167th will give us a value also in that same section, just higher up. Then when we subtract 1, as the question asked, we move one spoke over and land in the one where all numbers are divisible by 7. So the answer to the original question is yes, with no intensive work required. But here's the least intuitive property I'll discuss, which works since we're using a prime number of spokes, or 7 in this case. Take any number not divisible by 7, like 2, 5, 15, or whatever, and raise it to the 6th power, or 1 less than the number of spokes we have, and that resulting value will always land in the section that has a remainder of 1. This will always be the case with prime wheels. As in, if we had a 5-spoke wheel and took maybe 12 and raised it to the 4th, our prime number minus 1, the resulting value will definitely be in that same section that has 1 as the remainder, just like before. And also, like we saw earlier, we can do fast math and say that 12 to the 4th minus 1 is divisible by 5, because it lands in the divisible by 5 section of this new wheel. This is Fermat's little theorem, again written like this. To break this down, it says that on a wheel with a prime number of sections, any number we'll call a, raised to the power of our prime minus 1, will be in the same section as the number 1, so long as a is
Oh, the wheel has prime numbers. prime sections, which means that you're dividing by prime the wheel. The same section.
It's divisible by 5, because it lands in the divisible by 5 section of this new wheel. This is Fermat's little theorem, again written like this. To break this down, it says that on a wheel with a prime number of sections, any number we'll call a, raised to the power of our prime minus 1, will be in the same section as the number 1, so long as a is not divisible by the prime. So when asked something like, what is the remainder when 2 to the 100th is divided by 101, it's actually really easy. Since 101 is prime, then anything that's not a multiple of 101 raised to the 100th, or that prime minus 1, will be in the same section as 1, and thus that will be the remainder. Another cool property that works for any wheel with a prime number of sections is that if you take any number, raise it to that prime power, or 5 in this case, the results will be in the exact same section. And this kind of answers what we saw in the beginning of the video. You'll notice that on any section, every other number has the same ones digit since they're 10 apart. So like all of these numbers are ones that end in 2 or 7. Now we just saw that any number to the 5th stays in its own section on this wheel. So doing that operation either keeps the same ones digit or changes it by 5, such as 2 going to 7 or 7 going to 2. Except when you raise a number to the 5th, odds will stay odd and evens will stay even. Thus the second option isn't possible, and any number to the 5th will retain its ones digit as mentioned in the beginning. Now if we make a wheel of 12 numbers, some cool things come from it. One thing to note is that all the primes show up on only 4 spokes. The only exceptions to this are the numbers 2 and 3, which are the only primes on these 2 right-hand spokes here. Again, this is nothing deep, as with most of this video, honestly. It happens simply because the primes that make up 12 are only 2 and 3. So in those sections, as we add 12 and move up our wheel, the resulting numbers will all be divisible by 2 or 3. In fact, all the sectors that consist of composite numbers start with a number divisible by 2, 3, or both. The sectors with primes, on the other hand, all start with a prime number or the number 1. So this isn't groundbreaking or anything, but I find it to be an interesting way to just look at numbers and primes. Then going back, if we multiply 2 primes together besides 2 and 3, the resulting value will also be in the same sections as the primes, just filling in some of the gaps. But the weirdest thing is that any prime number squared besides 2 and 3 will land in this section. This means any prime number squared minus 1 lands in the next spoke over, or the section where everything is divisible by 12. I mentioned this earlier, but an even stronger case where any prime squared minus 1 is divisible by 24. If you want to know why, just know that p squared minus 1 can be written as p minus 1 times p plus 1. And on a number line, we can write p minus 1 and p plus 1 around the original prime p. Now, since p is prime, then it's not even because it's greater than 2, meaning that p minus 1 and p plus 1 are even or divisible by 2. But every other even number is divisible by 4, so either p minus 1 or p plus 1 has a factor of 4. It's easier to see this with examples, like if these numbers were 30, 31, and 32, one of the even numbers must be divisible by 4, which 32 is.
It's like you're creating frequencies on a cycle, and then you're making connections based on that frequency. That's what it seems like. So you divide by an arbitrary number, and then you keep track of the frequency of the cycle as it grows the circle. And then you can extract properties based on that. It's very interesting. Like the first thing that comes to my mind when I think about this is gravity. And the pattern of gravity. I wonder if there is something to do there, like something related to that. Because everything happens on cycles. And that's what gravity is a spiral. So this mimics this thing, the pattern. So I wonder what's the difference as well if you increase the number of divisions or you decrease the number. What the difference is on the properties of the wheel. Because here you could increase the size of the wheel by an arbitrary number, I think. Like any number you want. And instead of going from 0 to 11 on the first level, you could go for a lot longer and then increase after that. So I wonder if there is any like reasoning behind cutting by this amount of numbers.
Then of 3 numbers in a row, one of them must be divisible by 3. It's not p, since p is prime, so it's gotta be one of the others. This means that 2, 3, and 4 are factors of p minus 1 or p plus 1, and those multiply to 24. Thus 24 is a factor of the original number. Now earlier in the video I talked about dividing a number by 3, and as I'm sure many of you know, when it comes to 9 and 3, divisibility is actually really easy due to a certain rule. The rule is if the sum of the digits of a number is divisible by 9, then the number itself is divisible by 9, and the same goes with 3. As in 972 is divisible by 9 because 9 plus 7 plus 2 is 18, which itself is divisible by 9. The reason for this is I can write 972 as 900 plus 70 plus 2, which can break down further to 9 times 100 plus 7 times 10 plus 2. 100 can then be written as 99 plus 1, and 10 as 9 plus 1. Then if I distribute everything, we're left with this. These terms are both divisible by 9 due to the 9 and 99 in them. So in order for the entire number to be divisible by 9, the last terms combined must be, which are the digits of the original number. A slightly more official term for working with 9s, though, is the digital root. To calculate the digital root of a number, let me just show an example. If we want to find the digital root of 921, let's say, we just add the digits together, giving us 12. We then add those digits together, giving us 3. Once we're down to one digit like this, we have the digital root. The cool thing about this is that it tells us how far a number is from being divisible by 9, aka the remainder. In this case, we see that 921 minus 3 is divisible by 9, which you now also know because of the digit summation. Another property if we go to Brilliant Sight is that digital roots do not change when you add or remove 9s from a number. So like we saw 921 has a digital root of 3, yet so does 9,921, and 99,921, and so on. Adding 9s doesn't change anything. Which means this huge number's digital root is 3, and thus it is 3 away from being divisible by 9. And this just comes down to the fact that if we remove all the 9s, leaving us with 21, that's also 3 away from being divisible by 9. Then something even weirder is that digital roots multiply. As in, if you want to know how close this result is to being divisible by 9, you multiply the individual digital roots. Since these 9s don't matter like we just saw, we can remove them. This means the digital root of each number is 1, and thus when we multiply them, the final digital root is of course 1. So I don't know what this large value is, but I know if I subtract 1, it will be divisible by 9. And just because we've seen 24 come up in this video in a kind of surprising way, here's another example dealing with digital roots. These are the first 24 numbers of the Fibonacci sequence, if we exclude 0, where you add the two previous numbers to get to the next. And these are the associated digital roots. Strangely, the digital roots you see here repeat this pattern forever as you go through the Fibonacci sequence, reoccurring every 24 numbers. Not gonna go into more detail beyond that, but I just found that interesting. Now after all this, you may be saying, yeah, this can help me do fast math, but can it help me write secret codes? Okay, maybe you weren't thinking that, but still the answer is yes, like I briefly mentioned in the beginning. I've done an entire video on the math behind cryptography, but for those who just want to know how the things we saw here apply to encrypting messages, here's a quick explanation. First, just imagine a world before cryptography where you want to communicate with someone you've never met before, yet there's an eavesdropper in the middle of you two who can hear anything you say or see anything you do. My question is, how would you communicate a message to the other person secretly just by shouting over to them? I didn't have to pick these numbers, but I'm just using them for simplicity. So yes, you've said this out loud, which means the eavesdropper will be in on everything so far. But then you tell the person to think of a secret number and don't say it out loud while you do the same thing. So let's say they choose 4 and you choose 3. Now you do that base value of 5 to the power of your secret number, which gives us 125, and then you find the smallest number on that section of the wheel. With 17 numbers, 125 will be in the same section as 6, and 6 is what you tell the other person. Then they do the same by calculating 5 to the 4th, which is in the same section as 13 on our wheel, and they tell you that value. So now the eavesdropper has these two values as well, but not the secret numbers. Lastly, you take their value of 13 and raise it to your secret number of 3, and again, find where that is on our wheel, which is 4 in this case. The other person does the same, and they will guarantee get 4 as well. This number is then your secret key. We haven't shared a message really, but we have established a secret key that we can then use to encrypt messages. For example, now we could like shift the letters in our message by 4 to communicate, although no, that is not what modern cryptography does. What you saw was the basics of the Diffie-Hellman protocol, and the reason it works to establish a secret key is because it is easy to do the math you just saw forwards, but it is very hard for the eavesdropper to take the numbers he has and work backwards to figure out your secret numbers, and therefore the final key. Algorithmically, it would just take too long. Not with this example, but when dealing with numbers hundreds of digits long, going forward is doable fairly quickly, yet going backwards at the moment just isn't feasible in a short amount of time, so you can have a secure form of communication, even if someone's watching. But everything you saw was really just scratching the surface of this branch of math, but if you found this content interesting, I recommend checking out Brilliant's number theory course, where you'll learn a lot of the eavesdropper to take the numbers he has and work backwards to figure out your secret numbers, although no, that is not what modern cryptography does. What you saw was the basics of the Diffie-Hellman protocol, and the reason
Maths fans, welcome.
I think I'm just gonna watch more of these videos until I understand more how modular arithmetic works. It seems like it's very important for cryptography. And then I'll continue to review. I wanted to finish both of those articles today, but like there's nothing I can do about it. I have to understand first. Yeah, so like I can't force myself to understand faster. But I understand the theorem here is just the way that it's written is like annoying as all. This stuff here is very confusing. So I'm probably gonna rewrite this thing. But then to rewrite I need to understand like how this like the steps and the connection between them. Which it is hard for me to understand. It's more on the way that people explain that kind of annoys me. There's something about it. And it's not just this theorem, it's usually stuff involved with mathematics. Like, I always get the feeling that they are making it harder than it is. But maybe it's just my thing. Like the language of the way that these things are written, I don't like them.
Welcome to the next topic, topic O, modular arithmetic.
All right, here's the first video, Introduction to Modular Arithmetic,
Today we'll
and we just got
introduce
3 problems. Very basic. First problem. Today is Tuesday. What day will it be in 17 days? Now I know you can do this in your
I think I'm gonna watch the ones that are shorter first. I think I might stop here actually and just watch these videos off stream until I understand. And then after that, I'm gonna rewrite the proof here. I think some of the parts I'm gonna leave it like it is, but this part here I'm gonna change. Maybe I should ask ChatGPT, see if I can get a better answer as well. Yeah, blah blah blah. Yeah, watch one of these videos, and then I'm probably gonna stop and watch more of the videos and think about this off stream until I understand this.
This means when we have A is congruent to B mod n. And all the following are pretty much equivalent, and depending on situations, you can interpret them differently, okay? So perhaps the first thing I want to tell you is that when we have A is congruent to B mod n, this means that A and B have the same remainder. And I will put on quotation mark for the word remainder, because sometimes when we're talking about these kind of things, you may end up with negative remainders and things like that. So that's pretty much the idea. That's why I put on quotation mark. A and B have the same remainder when they are divided by n, okay? And by the way, n shall be a positive whole number greater than 1. So 2, 3, 4, 5, and so on. Do not ever say n is equal to 1. Mod 1 kills everything. Don't do that. Okay, you're pretty much just killing all the math, killing all the number series. So don't do that. Okay, so this is the first way to interpret this notation. A and B have the same remainder when we divide A by n, when we divide B by n. So that's the first thing. The second thing is that I can write the following. When we have A is congruent to B mod n, we can say A is equal to, well, it's just going to be off by a multiple of n. And usually we can just say k times n for some number k, which we don't know yet. Just keep it as it is for now. And then you add b to it. And you see, when you mod n, this right here stays as A. When you have k times n mod n, this is always going to be a multiple n, so it becomes 0 in the mod n world, and then you're left with the b right here, okay? So sometimes it may be helpful when you go from here to here, because from here, you're working with an equation rather than a congruence. So that's another way to use this notation, I would say, another way to interpret, another way to approach when you have a congruence. The next thing is that, okay, I can just subtract b on both sides, right? And if you subtract b on both sides, you can see that a minus b is equal to k times n. In other words, a minus b is a multiple of n, right? So I can actually go from here and tell you guys that n divides into a minus b. And once again, this right here has a few ways to interpret it. This is actually the common notation that we'll be using quite often. This right here, you say that's divides, okay? And when we write this down,
So this that he's saying is related to this stuff here, now I understand. because you can write this thing as the equation there, but I don't understand why. But because of the explanation, I understand now that it implies this thing here, because it's one minus the other.
This means, let me just put this down in blue, like why not? This means that a minus b is a multiple of n. Okay, so that's the idea. So that's pretty much it, right? I think this is just perhaps the most natural way to know what that means. And this right here is pretty useful when you're trying to solve for an equation from congruence, right? You change the congruence to equation first. And then this right here is useful when you're doing some proofs. And perhaps I will just give you guys a quick example, okay? So this is just a quick example. So let's do easy one, I would say. Let's say we have 10, okay? And that's congruent to 14. Mod 4. Is it? Yes, it is. Why? Because when you have 10 divided by...
I'll go back to when he explains this part here.
All the math, killing all the numbers, so don't do that. Okay, so this is the first way to interpret this notation. A and b have the same remainder when we divide a by n, when we divide b by n. So that's the first thing. The second thing is that I can write the following. When we have a is congruent to b mod n, we can say a is equal to, well, it's just going to be off by a multiple of n, and usually we can just say k times n for some number k, which we don't know yet, just keep it as how it is for now. And then you add b to it. And you see, when you mod n, this right here stays as a. When you have k times n mod n, this is always going to be a multiple n, so it becomes 0 in the mod n world, and then you're left with the b right here, okay? So sometimes it may be helpful when you go from...
I understand. So the remainder is the same. So it implies you can add that remainder to any number that is a multiple of n, and you represent that with the k. And because of this, you can pass the other a minus b to the other side. It's going to be equal to k times n, which is going to have mod 0 here. When divided by p, because p is the k on this example, is the n on this example. So it's mod p because k times p would have the remainder of 0. And here you just subtracted one from the other and then distributed the a outside. So I understand now. So maybe what I would do is explain this here. So he's saying that all the elements are distinct because if two of them are congruent, that it would mean this, which would, the consequence would be this. Let me think about how I'm gonna write this stuff. Harder. don't know how I should do this symbol here, so I'm just gonna copy. It's gonna be like very. It's not gonna be as concise as this, but it's gonna be a lot easier to understand, I think, if I write it like this. Because I'm kind of repeating myself here. It's not very. Like, this is more concise, but the problem is that it becomes a lot harder to understand. There's another way to write. Another way to write. This means that which is equal to remember this set contains p unique elements because in order for two of the elements to be congruent, IA would have to be equal to JA mod P. So this means the remainder of IA divided by the number P would be equal to the remainder of JA divided by P. If I less than J, this implies that J minus I, because another way to write is this one, where K is an arbitrary number. This means that which is equal to since A is not divisible by P, this implies that JI is not divisible by P. Now that's the part that I don't understand really well. Oh no, it's because the numbers are up to is equal. And since A is not divisible by P, this would imply that J is divisible by P. Which contradicts the assumption that this should define the sets. I think this way, I'm gonna leave it like this. But I don't understand really well why it is also clear that none of the elements of the set is equal to 0 modulo P. I think, yeah, I get it's because the multiplication is not going to be divisible by P because it's lower than A, yeah. So it makes sense actually. Since A is not divisible by P, then all the other numbers are not divisible by P either, the multiplication. So, and because it's a multiplication of this number with A, and neither of them is divisible by P, this means that none of them is going to have remainder 0 when divided by P. It makes sense. If A is not divided by P, then we can define the set modulo P. This set contains P minus 1 unique elements because in order for 2 of the elements to be congruent, I would have to be equal to J mod P. This means the remainder of IA divided by the number P would be equal to the remainder of JA divided by P, with I lower than J. This implies that, because another way to write is this, where K is an arbitrary number. This means that which is equal to this. Because the remainder of the division of both sides would have to be 0. I think here the problem is that I have to say that it would have to be equal to this, but it's not. Equal to the remainder of J divided by P. This would imply or maybe the other way that I wrote was fine. This would imply that for 2 of the elements should be congruent, so it should be equal to I think this is fine. It's a little bit confusing, but I think I'm gonna leave it like this. It's better than it was before, at least. I think. Like, it's confusing because it's explaining after, but I think that's fine, actually. Like, it makes a lot more sense now in my mind with this translation here. Like, I couldn't make this leap in my mind when I saw this thing here. But it makes a lot of sense. You're just adding the remainder to this number here, which is the same as writing this thing here. Does each element of the set is congruent to one of the elements, to one of the numbers, and no two are congruent to the same number? No two are congruent to the same number. Okay, yeah, that makes sense because they are unique, and they are congruent because they are multiplications of this. Makes sense. Now we multiply all the elements of the set together and obtain. Doing the factorial. This one I'm gonna put in cold brackets here. The left hand side can be written as this. I think this is multiplication here. Maybe I'll... Yeah, because you're distributing A, and you're gonna sum the... Because A is gonna be multiplied by itself by this amount of times, so it becomes the exponent. And the other, you're multiplicating the numbers. Yeah, the factorial of one is equal to the other, which proves the... I think I understand now, actually. So both of them are the factorial, which proves that after you simplify, we obtain the theorem. So the hard part was understanding this mods thing here. But I think I'm gonna stop here. I'm gonna watch the videos to understand more about it. And then tomorrow I'll focus on this one, extended Euclidean algorithm. Hopefully by then I'm gonna understand more how it works after watching a bunch of videos. It's difficult for me to think about this because I've never seen it before, this way of writing things. It seems more abstract as well, because you have to think about other steps to make it make sense in your mind. Blah blah blah. Linear theorem is a powerful tool in number theory, cryptography, and computer science. What I'm probably gonna do is just read this stuff and check to see if it's correct, and I'm gonna leave it like this. Or maybe I'm gonna remove some of these as well. Computer science, it provides a simple analog way to prove primality of numbers and has numerous applications in encryption, pseudo random number, areas of mathematics. By understanding the theorem, these applications, one can gain a deeper appreciation for the beauty. Yeah, I'm gonna stop here. Tomorrow I'll come back and I'll do this one probably. I will reveal the last of this stuff here off stream. Probably remove some of them or leave it the same because it doesn't matter that much. I think the most important part for me was understanding this part here, which I understand now. Just the proof of the theorem, like what it is and how it works. And I don't want to spend too much time on this because I want to understand the other stuff that is more practical. But obviously it's important to understand this because the other stuff is going to use this as well. About the cryptography in Ethereum. To understand the diff Halfman, or however say that thing there. And yeah, it's gonna take some time as well. I have to watch the videos, there's nothing I can do about it to understand faster. So I'm gonna do that off stream and then I'll probably come back tomorrow, continue to do these articles. So see you